LLM agents are rapidly evolving, but their reliability in long-horizon tasks remains a critical bottleneck. The core issue is that agent failures rarely originate from a single bad prediction. Instead, errors accumulate and propagate through interdependent reasoning steps, tool executions, and environment feedback. Current uncertainty quantification methods struggle here. They rely on local signals like token probabilities or predictive entropy, treating each step as independent. Or they model trajectories as linear sequences, ignoring the complex relational structure of agent execution. A mistake in step one might not cause immediate harm, but if it influences subsequent tool use or reasoning, the risk compounds. Existing methods miss this propagation. Enter RUPA, Relational Uncertainty Propagation for Agents. RUPA models the execution trajectory as a directed relational graph rather than a sequence. Nodes represent execution events, reasoning states, tool invocations, and observations. Directed edges capture logical dependencies between these events. RUPA defines 7 edge types to characterize these relationships: sequential, latest, repetition, progression, parallel, feedback, and goal alignment. The technical depth comes in how uncertainty propagates across this graph. Each edge is assigned a weight based on relation reliability, relation strength, and temporal decay. This ensures that structurally important dependencies exert greater influence on risk propagation, while obsolete states are discounted. For goal alignment, RUPA computes a specific score based on semantic similarity to the original task objective, independent of the standard edge weight. Uncertainty is then propagated by aggregating risk from neighbor nodes, weighted by these edge values. Crucially, RUPA maintains an exponentially decayed uncertainty momentum to preserve long-range execution trends. This allows early critical failures to continuously influence risk estimates for downstream nodes that depend on them, even if the current generation appears confident. The final risk score combines this propagated structural uncertainty with the node's local uncertainty. Evaluations on Tau-2, Terminal-Bench 2, and GAIA across 6 models, including QN and GEMMA, show RUPA consistently outperforms baselines like entropy, tracer, and SAUP. RUPA achieves superior AUROC and AUPRC, enables earlier failure detection by identifying risks before trajectory completion, and improves downstream task success rates when used for uncertainty-guided sampling. RUPA demonstrates that explicitly modeling relational dependencies is essential for reliable uncertainty quantification in autonomous agents. The code is available on GitHub. Make sure to check the description for the implementation and to build more trustworthy agent systems.